So S infinity equivalence relation is it clear? Of course it contains R. Now containing R. Now let sigma be, you can say let T be another equivalence relation containing R. Then what is our claim? Claim is what? That S infinity is the smallest equivalence relation we have to prove. So we have to prove that S infinity is contained in T. Correct? So T is till T be another equivalence relation containing R. That is, R is contained in T. We have this. R inverse is contained in T. R converse is contained in T inverse. T converse and T inverse is equal to T, since T is what? Symmetric. Also 1x is contained in T. So R is contained in T, R inverse is contained in T, 1x is contained in T, since T is what? Reflexive. Correct. So R union R inverse, that is S, is equal to R union inverse R 1x is contained in T. Correct. So S is contained in T. So it implies S square, that is S composition S, is contained in T composition T, and of course it is contained in T since T is transitive, because T is equivalence. So T is transitive. So Sn, it also implies that Sn is contained in T. It also implies that S infinity, that is union to 1 to infinity Sn, all are contained in T. So it implies that S infinity is what? Re, that is the smallest equivalence relation containing R. So in this way it is proved. Of course S2 is contained in T. Similarly we can prove, you can just write similarly Sn is contained in T, isn't it? Because S2 is contained in T, S cube, it will again contain in T due to transitivity. So we can prove that Sn is contained in T, and also S infinity, that is the union of all such relations, again contained in T. So in this way S infinity becomes the smallest equivalence relation containing R. So of course S infinity is equal to Re. So Re is what? That is Re is equal to R union R inverse union 1x infinity. So in this way it is proved. Now this proposition can also be rewritten in another form. that is proposition 1.4.10. That is, they are saying if R is a relation on a set X and R is the smallest equivalence on X, of course R is the smallest equivalence relation, it is on X, of course, containing R, then they are saying that same thing, that is X comma Y belonging to RE implies either X is equal to Y or for some n belongs to set of natural number, there is a sequence of transitions. There is a sequence of transitions X is equal to Z1 goes to Z2 dot so on, Zn is equal to Y, in which for each I in set 1, 2 dots on n minus 1, either Zi comma Zi plus 1 belongs to R, or Zi plus 1 so X comma Y belonging to RE, it implies either X is equal to Y or for some n belongs to natural number, there is a sequence of transitions. X is equal to Z1, Z1 goes to Z2, Z2 goes to so on, it goes to Zn is equal to Y, in which for each I in this set 1 to n minus 1, either Zi plus 1 belongs to R or Zi plus 1 comma Zi belongs to R. So both are same. If this theorem is rewritten like this, correct? So basically what happens, see how we do this. First we prove that R is, first we prove previous lemma, that is RE is equal to X comma Y belonging to RE. RE is what? R union R inverse union 1x infinity, that is the union of 1 to n R union R inverse union 1x ki power n, correct? Now of course this is the union of, for example, consider it total as S, so S ki power n, so it is what? S union S union S union S union S union union S union S union S union S union, like this or so on. So when you take X comma Y belonging to RE, it will go in this or not? Of course it implies and re-implies X comma Y belongs to union of 1 to n R union R inverse union 1x n infinity. It will go to this. It will go to I mean to say that it will go to like this: R union R inverse union 1x n. So basically it means what? This is what? R union R inverse union 1x. So basically what happens, either x comma y belong to 1x or x comma y belongs to R union R inverse. So basically what we write, it implies x comma y belongs to 1x or x comma y belongs to R union R inverse. X comma y belonging to 1x or x comma y belonging to R union R inverse की power n basically. So when x comma y belongs to 1x, it means what? That is x is equal to y. So either x is equal to y or x comma y belong to this, and this is what? This is what? This is basically R union R inverse, composition R union R inverse, composition R union R inverse. So it is how many times? N times. So x comma y, it means that, so or just I am writing like this, or this is equivalent to what? It means there exists z1 z2 dots on zn, or you can say that in between the elements come. So you can say that z2 z3 zn minus 1 in between the elements comes from x such that x is equal to z1. You say like this: z1 comma z2 belongs to R union R inverse, and z2 comma z3 belongs to R union R inverse dots on zn minus 1 comma zn is equal to y belongs to R union R inverse. Now you see, when z1 comma z2 belongs to R union R inverse, it means what? That is x comma z2 belongs to R. Here you can write like x is equal to z1 comma z2 belongs to R, or z2 comma z1 is equal to x belongs to R. That is z2 comma z3 belongs to R, or z2 comma z3 belongs to R converse, or you can say z3 comma z2 belongs to R. In a similar way, you can write here, that is zn minus 1 comma zn is equal to y belonging to R, or y is equal to zn comma zn minus 1 belongs to R. Now you see, so you are getting a sequence of transition: x is equal to z1, x is equal to z1. Now z1 is z2, z2 to z3, zn to y, in such a way that you see that zi plus 1 belongs to R, or zi plus 1 belongs to, it means what? zi plus 1 belongs to R converse, or you can say, just you can, if you merge it, zi plus 1 belongs to R union R converse. Correct? So in this way, this is the meaning of this theorem. We have to prove first. If this is asked in the examination, first you have to prove that RE is equal to R union R converse union 1x infinity. Correct. After that, you take element here. Of course, it will go in. It implies, re-implies. It will go. Both are equal to each other, so it will go in x comma y belongs to 1x, or x comma y belongs to R union R inverse n. Correct. It means that and this is n times, so there exists in between element. By the definition of composition, you will get elements z2, z3 dots and zn minus 1 belonging to x, such that in this way you will get, and in this way this theorem is proved. Correct. So this topic is finished, and in the next turn we'll start next topic, congruences. So we will stop here. Thanks.